I start recording. Okay. Thank you for reminder. Yeah, Len, please go ahead. Yeah, thank you.
Yeah, okay. So hello, everyone. I'm Sizheng Ma, a graduate student at Caltech. And today, thanks for inviting me to give this talk on the backwards one-body model. So to start with, let me give you an overview on what this model is about. For gravitational wave emitted by a binary black hole system, it consists of in-spiral merge and Ringdown. And there are some standard methods to treat each region. For example, the post-Newtonian theory works well for the in-spiral part. The Ringdown part can be described by black hole perturbation theory. And the merger is highly dynamical, so we really need to use numerical relativity. So the Bob model, the backwards one-body model, whose abbreviation is Bob, is the 10-domain waveform model for late merger and Ringdown, proposed by Sean back in 2018. So in this talk, I will be talking about this model, but before going into the details, I should emphasize that the study of this Bob model is still at a very preliminary stage. So far, there is only one paper about this, and so this model could end up with a merely phenomenological model that happens to agree with numerical relativity, or it could be possible that there are some deeper physics behind this. So far, we still don't know the answer. And my current understanding of this model is also naive. As I shall mention later, there are a few phases along the line of the reasoning that I don't understand or disagree. Yeah, so this is a chance for me to have discussions with you guys. So in the first part of the talk, I will show you how Sean McWilliams built this model. And in the second part, I will be talking about its implications. The basis of Bob model relies on the connection between the quasi-null mode and the lightning. The quasi-null mode is a very important concept from black hole perturbation theory. It is related to eigen oscillations of a black hole. Last year, I talked about the oscillation of a neutron star. We know within Newtonian theory, oscillating star doesn't emit gravitational waves. So the system is self-adjoint, which implies that eigenmodes of the star are real, complete, and orthogonal to each other. So they are called the normal modes. But within general relativity, we know an oscillating black hole may emit gravitational waves. So it means that an eigenmode must decay over time. Its mode frequency must be complex. In addition, the system is not self-adjoint. Different modes are not orthogonal and they don't form a complete basis either. So they are not normal modes anymore. Instead, they are called quasi-normal modes. From black hole perturbation theory, we know the radial direction of the equation is a wave equation. Here I'm showing the potential of the black hole, where the R star is the tortoise coordinate. A quasi-null mode is a solution that has only the outgoing part at infinity and the ingoing part at horizon. By the way, this minus infinity represents the location of the horizon. So one can, of course, solve the equation numerically and find the values of quasi-null modes, but it turns out that there is a simple and semi-analytic method to understand the physics behind quasi-null modes. It is called WKB approximation. So below I will give a quick introduction to this method. Let's first think of the simplest system, namely a free quantum state. Then we can ask what is classical limit case. So we can the correspondence principle tells us that we need to take this h bar to 0. But if we naively do this, the system is reduced from a second-order differential equation to an algebraic equation, and there is only a trivial solution. So a correct way is as follows. We can first write the wave equation in this form, and the filter is expanded in terms of h bar, and the leading term has a negative power. After some calculations, you can show that this filter satisfies the classical Hamilton-Jacobi equation, so it corresponds to the action. The other example is for the geometric optics. So we know an electromagnetic wave is given can be described by the Maxwell equation, but in the short wavelength limit, it can be treated as a light wave, which satisfies the Fermat's principle. And still, you can use a WTB approximation to bridge both sides. Similarly, for a Poisson mode, we can use WKB approximation to treat as a light wave. So, and we know that a light wave near a curved black hole is non-geodesic. So then it's important to understand the feature of non-geodesic around curved black holes. Here I don't want to show the full equations of motion of a non-geodesic. Instead, I want to use the more physical tool to help you understand the process. This tool is very simple and it is used widely in high school physics. But on the other hand, this tool is very powerful that we can use it to handle any situation. Let's imagine a small ball rolling on a frictionless surface. So the total energy of the system denoted by E is conserved. It consists of the kinetic part and the gravitational potential. So if we know the shape of the potential and the value of the energy, we can already know some information about this. Will oscillate within this region, and it cannot go beyond this energy level. Especially this happens if we shift this then
we lost the screen, yeah.
Then in this system we know.
Can you hear me? I think we lost your screen, yeah.
Yes, I can hear you. Can you hear me?
Yes, I can hear you, but it seems we lost the screen, yeah. I don't know if others can see your screen or not.
No, we can't. In fact, it's breaking up a bit. So
yeah, it's a break. It become screen become break. Yeah. Yeah. Can you share again and we can see?
Sorry, let me. Oh, sorry, my laptop seems to be frozen.
Have you shared a screen?
No, sorry. Can you hear me?
I think the connection is not smooth. Yeah, I think. Hello? We can see the slide up. Yes. Yeah.
Okay. Great. So I think, yeah, I was interrupted here. So basically, if we, I was talking about this simple to understand the null geodesic around the curve black hole. And so if we know for a small ball rolling on a frictionless surface, once we know the shape of the potential and also the energy level, we can know its motion oscillates within this region. But if we shift this energy down here, then we know this ball just stays here and it cannot move. Other scenario is like this system. If we flip the potential downside bar, then the allowed motion is limited to either left-hand side or right-hand side. So below, I will be using this to understand the null geodesic of a curve black hole. For any geodesic, it always has 4 first integrals: the total energy E, the orbital angular momentum projected to the spin of the black hole. The third one is called the Carter constant, and I'll show you its physical meaning soon. The final one is the length of the geodesic. For null geodesic, its length is always 0. So with these 4 first integrals, we can always separate the equations of motion into each direction, including the temporal part, the radial part, and the 2 angular parts. In particular, in the polar direction, which is this theta, the effective energy in this direction is called the Carter constant. And for a null geodesic around the curve black hole, its potential can be classified into 2 scenarios. In the first case, here the theta equals to 0 means the north pole, pi means the south pole, and pi over 2 means the equatorial plane. So if we put the Carter constant here, we know the null geodesic will oscillate within this region from the north hemisphere to the south hemisphere, back and forth. If we shift the value of the Carter constant down here, then we know the only allowed motion is a stable motion within the equatorial plane. In other scenario, we have this kind of potential. Again, if we put the Carter constant here, the null geodesic will oscillate between the north and the south hemispheres. Again, if we have this special system, there is an unstable motion within the equatorial plane. If we further lower the value of Carter constant, the null geodesic will be limited to either the north hemisphere or the south hemisphere, and it cannot cross the equatorial plane. In the radial part, the potential always looks like this. The shape is controlled by the LZ and the Carter constant, and the effective energy in the radial direction is controlled by both the total energy and the Carter constant. But here I just omit the Carter constant for simplicity. And you can already know that the shape of the this potential is akin to the potential from the black hole perturbation theory, which is on the left. And let me remind you again that a quasi-null mode corresponds to a solution that has only outgoing component at infinity and ingoing component at horizon. So what does it mean for a null geodesic? Let's first look at this system. If we put the energy level here, then the null geodesic is limited to either right-hand side or left-hand side. Neither of them can satisfy the boundary conditions at both sides. So this is not what we want. Then how about this scenario? In this case, the null geodesic is allowed to travel across the entire domain. It could either force from the infinity to the horizon, or it could be emitted from the horizon to infinity. One may ask that how come a black hole can emit something? Well, if you are familiar with the maximum extension of a curved black hole, you will know that this solution corresponds to a spinning white hole rather than a black hole. Again, we cannot have desired boundary conditions at both sides. The only possible system happens if we put this total energy to the maximum value of the potential. Then you can see there is an unstable motion here, and the light is trapped at a fixed radius. So it is called light ring or photon sphere. And since it is unstable, under some perturbations, it can either fall into the horizon or escape to infinity. And the escape part corresponds to the ringdown observed by us. So in this way, we can construct a map between a quasi-null mode and a class of null geodesic. For a quasi-null mode, it is labeled by 3 indices, M, L, and N. Here N is the index for the overtone. And for a null geodesic, it is accompanied by 3 first intervals, LZ, the Carter constant C, and the total energy. So from quantum mechanics, we know M always corresponds to LZ. And the total angular momentum squared is roughly equal to L times L plus 1. For a null geodesic, we can decompose this L squared into a Z component and the parallel component. And recall that the Carter constant is the energy in the theta direction. So we can make a connection between this Carter constant and the parallel component. Finally, the real part of the quasi-null mode frequency corresponds to the energy. I should emphasize that not every null geodesic has its quasi-null mode counterpart. It has this correspondence only when we have this special configuration. So for a Schwarzschild black hole, the light ring is at 3n. So another important orbit is called ISCO. It is related to a time-domain, time-like geodesic. I have mentioned that when the light ring is perturbed, part of the wave can escape to infinity and become become ringdown. So it is important to understand how a light evolves when it is perturbed from the light ring. So a way to analyze the problem is to give its initial position a small offset and see how the deviation from the unperturbed solution evolves. For example, we have this unperturbed version, solution 1. If the deviation always remains bounded, like this solution 2, this solution is stable. But if the deviation goes exponentially, like the solution 3, then this motion is unstable. The coefficient in front of time is called the Lyapunov exponent. For a null geodesic around a curved black hole, it turns out that its angular direction is stable, but radial part is not. It is given by a sinh function. So far, my description on this page is fully geometric. But in order to have a better understanding of the Bob model, this picture is not enough. So we should go to next to leading order WKD approximation. At this order, the approximation tells us how the wave amplitude evolves. Let's think of a family of nodes whose motion is unstable. So we know its cross-section evolves over time. And the WKD approximation tells us that the energy should be conserved, which is given by a product between the product of amplitude squared and the cross-section. So once we can get the evolution of cross-section from the leading WKD approximation, we can then get the evolution of the amplitude. So having provided some relevant backgrounds, let's start to look at what the Bob model is. The core idea is that it is as follows. When two black holes get very close, the outer space-time can be treated as the remnant black hole plus some perturbations. And in fact, this idea is not new. For example, this famous closed limit approximation also uses this idea. So people proposed this closed limit approximation before the success of merging two black holes through numerical relativity. Since the problem was very difficult, people were thinking about some other alternative approaches to get Ringdown signals. So within this closed limit approximation, when two black holes get very close and the common horizon is about to form, the outside space-time can be treated as a remnant black hole plus some perturbations. So once we can construct some Cauchy initial data on a Cauchy surface, then we can evolve that initial data by using the black hole perturbation theory. In this way, we can get an approximation for the Ringdown signal. Within the closed limit approximation, the data was constructed analytically, whereas in the Lazarus project, the data was constructed numerically. Similarly, for this Bob model, once we have the remnant black hole plus some perturbations, and from my previous arguments, the perturbation near the lettering will partially fall into the black hole and partially escapes to infinity. And this part corresponds to the Ringdown signal observed by us. And from the next to leading order WKD approximation, we know how the amplitude evolves over time. So in this way, we can construct a waveform model for gravitational wave. This is the core idea of the Bob model. Below, I will give you some more details. So let's look at a family of lattices within this red region. Since its angular motion is stable, and but the radial part is not, as they escape to infinity, its radial separation gets prolonged. So the cross section is proportional to delta r. From WKD approximation, we expect that the amplitude squared times the cross section, namely this delta r, should remain constant. But in the Bob model, Sean-McWilliams argue that one should use this relation, namely the amplitude times the cross section, to be a constant. There were only a few sentences about this relation, and no mathematical derivation was provided. So this is the first place that I got confused. But for the moment, let's accept his argument. So the amplitude of the gravitational wave should go as 1 over delta r, which is this Sizheng function. But for the moment, we still don't know it is whose amplitude. It could be the waveform h, or its first time derivative called the News function, or the second derivative called the Weyl scalar Psi4. After some numerical experiments, Sean Williams found that Psi4 agreed the best. So we end up with this relation. And namely, the amplitude of the Psi4 is given by this Sizheng function across the lazy merger and Ringdown. But then how about its phase? His construction was based on an empirical relation from this paper. So this relation makes a connection between the phase evolution and the amplitude evolution. And the coefficient is roughly insensitive to time. So far, I still don't have a good intuition on this relationship. But by combining this relation with the amplitude of Psi4, we can get the evolution of this phase. So at the end of the day, we can combine those two results, and we can have a complete ball model. So I took this plot from his paper. This is a comparison between the numerical relativity and different models. The ball model corresponds to this black dashed line, and you can see it is the best one. Okay, so I have gone through all the information I know about the ball model. Next, I want to discuss some implications of this model. The first part is called collective excitation of overtones. So we know the amplitude of Psi4 is given by this Sizheng function. So we can tailor expand it near the peak of the waveform. And the result looks pretty interesting. So you can see each term is an exponential decay. And the decay rate is the same as the imaginary part of the nth overtone predicted by the WKB approximation. So we can identify the Taylor index n with the overtone index n. This fact implies that overtones are excited in a way such that they can be resound into a single time domain function. And then next we can see this -1 to nth power. It implies that adjacent overtones contribute destructively. We have 1 minus 1, 1 minus 1. And I will show you later this relation does hold in numerical relativity waveform. But on the other hand, it seems that the Bob model impose too strong condition on this on the overtone amplitude. So in fact, it requires all the alpha n to be 0 and to be 1, meaning that all the overtones are equally excited. And I will show you soon that this is not true. So this is my second confusion. Why does Bob work pretty well, even though it requires all overtones are excited equally? So let's look at extreme mass ratio in spirals. The Ringdown of memories can be written as a superposition of different overtones. And the mode amplitude can be computed from black hole perturbation theory. In particular, it consists of two parts. The first one is called quasi-null mode excitation factor. It is fully determined by the nature of the primary black hole. So it has nothing to do with the orbital dynamics. The second term is called the source factor. It contains the information about how the small particle plunges into the primary black hole. So using black hole perturbation theory, we can compute the excitation factor as a function of overtone index for different curved black holes. I took those results from a recent work by Oshita. Sorry. So, oh, sorry, can you still see my screen?
Yes, I can see the screen. But
Oh, okay,
sometimes
okay.
it break out. Sometimes they break out for 1 second.
Oh, okay.
Yeah. Do you?
Okay.
It's also on your side?
Yes. So can you see my cursor here?
No. Yes. Now I can see the cursor. Yeah.
Okay. Okay. Great.
Yeah.
Okay. So I took the plot from the paper by Oshita, and you can see the dependence of the excitation factor on the overtone index is not flat. It has a peak around n equals to 5. So it is contradictory to the prediction of Bob model. But on the other hand, still from this paper, Oshita showed that the source factor is independent of overtone index. So as a result, we can factor this term out, and the remaining piece is a function of time, which is independent of orbital dynamics. This fact agrees with the feature of Bob, because Bob also uses a single time domain function to describe the time evolution of a waveform. And the information about orbital dynamics appears as an overall factor in front of this time domain function. In addition, let's look at the phase of the excitation factor. So you can see we have two branches. The upper branch corresponds to even overtone indices and vice versa. So and the two branches differ by time, roughly speaking. So this part is consistent with the prediction of Bob model due to the factor -1 to the nth power. Okay, so the final part of the talk is about something broader. So here I want to take a step back and discuss the black hole spectroscopy and make connections to the Bob model. The idea of the black hole spectroscopy is pretty straightforward. If people can detect one quasi-null mode from a Ringdown signal, then we can infer the properties of the remnant black hole, including its mass and spin. If multiple modes are detected, people can use them to test the no-fear theorem. But to do so, there are some questions that we might want to address. For example, when the environment near the black hole is not empty, let's say there is an accretion disk. What's its impact on black hole spectroscopy? How do quasi-null modes change with those perturbations? And are those changes stable? Are the quasi-null modes the feature of black holes? So basically, those questions can be classified into two scenarios. The first case is about a bumpy black hole. In this case, the black hole potential is modified from the outside by some environmental effects. The second case corresponds to modifications from the inside. For example, if there are some quantum effects near the horizon, there is a reflective surface that can reflect incoming gravitational waves. It could be also a very compact black hole mimicker whose surface can also reflect gravitational waves. Under these two, in these two scenarios, the value of quasi-normals must deviate from their black hole counterparts. And it turns out that the quasi-normal spectra are unstable. The instability can be divided into two classes. The first one is called the migration instability. To understand what's going on here, let's first recall the definition of the quasi-normal mode. So we have asymptotic behaviors at both boundaries. Here we are interested in its radial behavior. So the radial part can be written as like e to the minus omega I times r star at infinity. Here omega I is the imaginary part of the quasi-normal frequency, which is negative. Near the horizon, we have e to omega I times r star. So you can see at either side, the eigen function of this quasi-normal mode actually blows up. Any tiny perturbation at infinity or at horizon can lead significant change to its eigenfunction. As a result, the mode frequency will also be changed significantly. This phenomenon is called migration instability. This instability already looks pretty strange. It says that a perturber, if a perturber is far away from the system, it has a huge impact on eigenmodes of the system, which is very counterintuitive. The second part is the second type of instability is called overtaking instability. So to understand this type, let's imagine a black hole mimicker with the perturbation from the inside. As a small particle falls into a black hole and hits the peak of the potential, it generates the Ringdown signal. And as it keeps falling into the system and hits the surface, hits this reflective surface, a part of it can be reflected and coming out. Part of the way can penetrate the black hole potential and escape to infinity. And this signal is called echo. The whole process can repeat itself, and we can have a series of echoes at infinity. For this new system, we have a family of a new family of quasi-normals, which corresponds to a trapped modes within this cavity formed by this reflective surface and the peak of the potential. This family of modes don't have their black hole counterparts, so they represent other type of instability. This plot summarizes two instabilities. Here I'm pointing at the original quasi-normal of a regular black hole. Oh, by the way, the y-axis is the imaginary part of the quasi-normal, whereas the x-axis is a real part. So if we turn on the perturbation gradually, its mode frequency can drift along this black hole. So it corresponds to migration instability. Meanwhile, we have a bunch of new modes in this region. They correspond to the trapped modes. And then let's go back to the idea of black hole spectroscopy and ask if quasi-normals are highly unstable and they are sensitive to some environmental effects. Does it mean that gravitational waves emitted during Ringdown will be totally different? The answer is no, because the time domain response has very different feature from the quasi-normal spectrum. And let's still look at this black hole mimicker. And a small particle falls into this system. As it hits the peak of the potential, an initial time response is generated. At this moment, this small particle is still causally disconnected with this reflective surface. So it doesn't know whether we have this surface or not. As a result, this initial time domain response is identical to the response of a regular black hole. As it keeps falling into the system and hits this reflective surface, a part of the wave can be reflected. Yes, so once this reflected wave hits this peak of potential again, we have the first echo. So we can see even though the quasi-normals of the system are changed significantly by this reflective surface, the initial time response still remains unchanged due to causality. The new quasi-normals appear as a series of echoes, and they don't come out until the Cauchy data, the initial Cauchy data travels across the entire domain and figure out conditions at both boundaries. As a result, those echoes are well separated from the initial time response, and the amplitude of the echo is much weaker than the initial response. In this sense, the time domain response is stable. By the way, there has been some effort searching for echoes in LEGO data, but no exciting news yet. So from my discussions, you may have already felt that the black hole, this binary black hole Ringdown has nothing to do with black holes and horizons. It is a common feature for lots of systems that have lacking. For a black hole mimicker, it is the echo that contains information about its quasi-normal modes. Whereas for a binary black hole system, it is just the horizon of the black hole observes everything. So we don't have any following feature. Then let's take a step back and recall people's current treatment of this BBH Ringdown. It was found that the BBH Ringdown is consistent with the sum of overtones starting from the peak of the wavefall. But from the line of the reasoning, it seems that it seems a little bit strange to do this mode decomposition. This decomposition is the correct way, but it is not the most natural way. So do we have a better basis to reflect what's really going on here? We still don't know. But on the other hand, the Bob model doesn't evolve this quasi-normal decomposition. It is a 10-domain waveform model constructed based on the response of the lightning on their propagations. And it happens to agree with the sum of overtones. The collective excitation of quasi-normals are one of its implications. So even though there are some problems with Bob for the moment, its idea is very inspiring. So at the end of the talk, let me summarize the problems of Bob model. First, which relation we should use for the WTD approximation? Should we use the amplitude or amplitude squared? The second is the prediction of the Bob. It is about the equal excitation of overtones. Okay, so let me leave this page here and take any questions. Thank you.
Yeah, thanks. Thanks very much for a very pedagogical introduction to this Bob model. Yeah. So now we open to the audience for questions. Please just raise your hand or just voice out if you have any question. Yeah.
Yeah, I can ask regarding this excitation of overtones. You mentioned that all of them are not equally excited. Is this the case for black holes, or you're saying in general for black holes with some kind of matter that is assumed outside?
Oh,
I mean, that was
so that excitation factor is actually independent of the source term, right? So what I'm showing here is the excitation factor coming from associated with a Kerr black hole. It has nothing to do with orbital dynamics or the property of the source.
okay. So it's independent of the part where you were talking about echoes and I mean, this migrant instability. It has nothing to do with that. It's just a property of just perturbations of a black hole of an ordinary black hole.
Okay, for that part, I'm not very sure. It could, so for example, for a black hole mimicker, I would guess that the excitation factor will be very different. So what I was talking about is we have a black hole and any kind of matter falls into the black hole, then we can have this excitation factor. But if it is replaced by other like black hole mimicker or some environmental effects, then I guess this excitation factor will be changed a lot because the quasi-normal mode may not be the most natural basis.
Okay. So essentially then this equal alpha n contribution that you spoke about,
Yes.
this is coming because of taking the negative, or I think it's called the negated Posh-Teller potential exactly. I mean,
Yeah.
the psi4 is taken to be exactly this form. You're saying in general it should not be of this form, then it should be some corrected Posh-Teller potential in order to give you the right alpha n's?
Well, this is the part that I feel pretty confused about. On the one hand, on the one hand, we have this comparison, right? We can fit this search function to the waveform model, and you can see it agrees pretty well. But on the other hand, if you compute the excitation factor from black hole perturbation theory, you will find out that the spectra are not flat. So it seems contradictory. So for the moment, I don't have a good answer for this.
Okay, and I actually just wanted to ask another a question related to this. So when you say it fits pretty well, is there a measure by which we can see it fits pretty well? So let's say I make these plots and I compare it with the actual results, and you see that it's nearly overlapping, but to what extent do I say that it's fitting really well? Like, what is the sigma errors and all that are being used to check how well it fits? I mean, the techniques.
Okay.
I mean, that's all.
So, for example, in this case, there is no sigma related thing. So you can just do this comparison across different models, and it happens to. It turns out that this Bob model gives the most accurate result comparison
out of the known models, out of the known techniques.
Yes.
Okay, and the last question I wanted to ask was, there are these earlier results which were done by I'm sorry, my memory is escaping me, but it's by Thorne, and it's on the transient dynamics from inspiral to plunge, and it's about I forgot who the second author is. I'm sorry, but it's about where an inspiral given a binary system, the transition from in-spiral to plunge has this transient behavior in the middle. So it's not exactly, I mean, that provides a sort of correction to your normal way of just matching at the light ring. Like it's not simply at the light ring, but you have this transient behavior, which is a little different. Do you think that that would play an interesting role here in correcting this Posh-Teller to another kind of potential? Possibly.
It's off song.
Sorry,
Oh yeah, sorry. It's Ori and Thorn from the 90s in 2000. So they basically found that there is this behavior as the black hole is transitioning from in-spiral to plunge, and it's literally called transient motion. So it's not exactly characterized by exactly what's happening at the light ring. There is some lagging and trailing behavior which is there across the light ring for this perturber that is falling in. But these are not considered, for example, in DOB. But these were considered in these sort of, analytical approaches to this transient. So do you think those inputs might help correct this? Because I see that as providing corrections to this alpha n, for example. You don't have a perfectly symmetric situation going along like in the Posh-Teller case. You have this trailing and lagging behavior, which highlights certain properties before the light ring and after the light ring, and certain modes may be excited differently.
Right. So I know the paper you are talking about, but sorry, I haven't looked into details about that paper. So for the moment, I don't have a good comment on this, I guess. But I guess in that paper, it was mainly about the Emery system, right?
No, it was just actually equal. Yeah, so it was like small mass ratio, but not Emery in the sense of. And so the small mass ratio allows you to take an adiabatic approximation in the in-spiral phase. But even if you take this adiabatic, in-spiral which is taking place, you couldn't exactly say that, okay, I start with some perturber which is starting at the light ring and it goes in quite like how they do in DOB. What they showed is that there is this transient behavior which takes place across the light ring. So this idea of just starting with boundary conditions at the light ring and going inwards may not be perfectly correct. Like you have the small correction which is there. And I think that might need to probably be factored into the DOB analysis.
I see. Okay. Thanks for pointing out.
Yeah, no problem. Thank you.
Yeah, I have two questions. Yeah. One is like this alpha, and theoretically, we need to fix this alpha. Normally, we fix the alpha and by matching this by matching with this merger or in-spiral fields, right?
Yeah.
Yeah.
Yes. Yeah.
So in some sense, in this part case, is from what you talk, I understand it like it's just a guesswork in some sense, right? Or
I'm sorry. It's what?
It's in some way. How do we? In some way, I'm not so clear how we get this hyper function waveform.
Right. So I guess basically we can have this search function here, and meanwhile we have a coefficient in front of this.
Yeah.
And it contains the information about the orbital dynamics. Basically, so
I mean, my question is that he didn't need to any kind of the. I originally think in order to determine the alpha, and in some sense we need to match in the Ringdown phase waveform with the one from the in-spiral and the merger, right?
Yes, but in that case, you are still using this mode decomposition. But instead, you can directly fit this search function to the entire time evolution.
I see.
And find the best the best parameter appear in here. So in the bulb model, we don't really have to determine alpha, and it's just so there are some free parameters in the bulb. Here I'm just showing you that if you further expand them, they are consistent with the sum of overtones. But from the bulb, we know different overtones are correlated, such that they can be resummed into this single tandem function.
So how we determine this hyperfunction, this waveform from the bulb model?
You mean how to?
This single H function. How do we derive this without using the without using, in some sense, without using the boundary condition?
You mean how do we get this section?
Yes.
Oh, so yeah, from this argument, right? So we know the next to leading order WKB approximation gives us how the amplitude evolve over time. It is related to the evolution of the coarse section. So in this case, we have a family of null rays, and its cross section is proportional to the radial separation. And if you perturb this,
I see.
the null geodesics around the lightning, you will have.
So this so in some sense, this null geodesic congruence you determine from near the black hole. And then he conjecture this A1 sigma 1 is A sigma conserved. Then he can derive the A.
Yes, as 1 over sinh, which is this search function.
Okay. And the phase cannot be determined or not.
Well, the phase part cannot be determined, and so it comes from this relation.
I see. And the second thing is the second question is related to this. So you are talking about this bulb model in some sense is kind of the time domain response, right? And
yes.
The response, you mean that you just perturb the trajectory and see the congruence data R, right? It's what this you mean. Yes. I see. And so in this sense, it is a little different from what quasi-normal we are dealing with.
Right. Exactly. So that's
in some sense that we can use in sometimes in WKB, the quasi-normal can also be think about some null geodesic in some sense. Can we make this comparison?
My
question may be not so clear. So in sometimes when we do this quasi-normal, we can also using this orthogonal correspondence to map to the geodesic equation, right? Can we understand the quasi-normal order from this kind of perturbation point of view? And then make connection about these two pictures. Originally, this what I think when we read the paper, this seems what the PRO paper suggests.
Yes. So this bulb model is based on this WKB approximation. How the light evolves when it is perturbed from the lightning. But I'm pretty skeptical about the idea that you can directly make connection with quasi-normals because, for example, quasi-normals are unstable.
Okay.
So when you do some perturbations, you basically screw up the whole quasi-normal spectrum, but its time domain evolution is stable.
I see.
The perturbations will appear as echoes. So the initial time response, which is given by this bulb, remains unchanged. So in this sense,
it is because you are considered the mimicker. It's not really a black hole. Then you get this stability. If I think about without this potential for the mimic, in some sense the ingoing mode will just directly go into the black hole without response back, and then this will cause instability, like we have quasi-normal mode.
Yes, but then in this case, it's pretty tricky to make connections with the new quasi-normals and the bulk, right? So I was trying to argue that when you perturb the system a little bit, quasi-normals will be totally different, but the time domain response will remain almost unchanged. So on the one side we have quasi-normals, and on the other side we have this time domain evolution and the Bohr model. Well, you can make connections, but from the behavior, from their behavior on the perturbations, I'm pretty skeptical about.
But can you go through your argument even without introduce a mimicker? I mean, if we really check for curved black hole, can we also see this time response is also stable?
Yes. So on the one hand, you can consider the environmental effect, right? So it is not necessary to be mimicker. Once you have like a Christian disk, for example, there will be other bomb here.
I see.
And in this case, the whole quasi-normal spectrum are also different. So I guess a way to think about this, question is that we have quasi-normals as bases, right? So they might not be the most natural basis to decompose the Ringdown. So what we want to do is to regroup them to a bunch of subsets and resound them into in either time domain or frequency domain. So we can get a bunch of new bases. And for example, this Bohr model corresponds to the leading term of this basis, and it is a time domain model. So I guess the real problem is to figure out the fundamental basis for the Ringdown, because from this behavior under perturbations, quasi-normals are unstable. So
it's unstable in the sense, right? I mean, it's unstable in the good sense. It finally will decay away, right? You are suggest that they are growing more, or usually we think
they are unstable in the sense that their values will be changed completely if we turn on the perturbations.
Okay, I see.
Right. So, for example, we have this regular black hole without any perturbation, and if we turn on, for example, the second bump at infinity due to a Christian disk, then its value will drift along this line. So we basically lose the information of the original black hole. But even though the time domain response is still stable, the initial time response is identical to the original system. So in this sense, we might want to use a different basis to describe the whole phenomenon. So this mode decomposition might be, I mean, not the most natural way, the fundamental way.
So here you
can I ask a very quick question? I can
ask
ask later, but it's fine. It's just regarding this correction to Post-Teller. That is what's happening here. Yes, like there is. So is there an understanding of what matter distribution or what kind of matter distribution profile, that is to say the density profile around a black hole, would give you this correction? And then do they match with certain accretion disk profiles that we currently already know?
So far, the study on this is pretty trivial. So they just assume some form of potential, the additional bump.
Potential correction, right?
Yeah,
but that should certainly be constrained by known matter distribution profiles around a black hole, right? Like we can talk about thin disks and thick disks, and we know what the density profile is like, whether it's self-gravitating or not self-gravitating. So, I mean, that this is basically an additional gravitational source correction to the black hole, and that has to come from some localized density distribution around the black hole. So that has not been done, is what you're saying. Like they've just considered the possibility of correcting the potential.
Yes, to my knowledge, I think this paper is last year, right? So the study on these directions. Actually, if I remember correctly, there were 2 papers in 2016 from Cardoso group. They were discussing the environmental effects on the quaternion modes. I don't remember whether they make connections to the real density profile. I need to check that.
Okay, thank you.
So, more questions? Yeah, I think if there's no more questions, we can stop here. Okay, and we thank Sizheng again. Yeah.
Okay. Thank you.
Yeah, still a lot of questions, but we can still chat if you like to stay a little bit. But it's very late at Caltech at California, right?
Yeah. Also, I think if we like get the our understanding of this right now is very poor, and we're trying some things. But maybe if we figure some things out in the short term, then maybe we could communicate and have a sharper question.
Yeah,
sure.
Especially regarding this BOB.
Yeah.
So probably we can
thank you so much.
Some chat later on. Yeah.
Okay.
Yeah. So thank you very much. Yeah.
Thanks for inviting me.
It's very nice. We learned a lot. Yeah. So if there is no question, then we will end here. Okay. Yeah.
Okay. Then see you later. We can chat through email.
Okay. Sure. Okay. See you. Okay. Bye.
Yeah. See you. Bye.
Bye.